In the previous video, we just had a single input and a single output. In other words, we could plot the input on the x-axis, output on the y-axis. In fact, we call the inputs and outputs x and y. Let's now look at multi-input, one output. Okay, just because that is illustrative of slightly more um, well complex functions, I guess. Um, let's first do a single layer neural network. The two inputs are x1 and x2. Okay, and we are saying that x1 and x2 can take values between -10 and 10. Of course, there's just two numbers coming in, but we are now, because we want to plot this function, namely the output as a function of these two inputs, um, we are just going to loop through different values of x1 and x2. Um, this command mesh grid essentially allows us to construct x1 list and x2 list, or x1 grid and x2 grid, which if you take any pair of x1 and x2 in this range, all such pairs are basically contained in x1 grid and x2 grid. So mesh grid is a command that allows you to um, very quickly loop through all possible sort of combinations of x1 and x2, where x1 is drawn from -10 to 10, x2 is drawn from -10 to 10, with 20 grid points in between. Okay, so that's what mesh grid allows you to do. In any case, we're just going to do a single layer network. In other words, these two numbers are going to come together. Um, you're first going to apply a linear transformation, right? So this is your W naught, W1. Let me just say that's W naught, W1 is 2, W2 equals 0.5. Okay. And then this is W naught, W1, W2. So we're going to first apply a linear map. I'm going to section this off. And then we're just going to plot z versus x and y. It's just going to be a plane. Okay. Let me run this first. Then we're going to apply plot z versus x and x1 and x2, I suppose. It's just this plane. Okay. A linear function of x1 and x2 and how many other inputs you have is a plane. Okay. Can rotate this around and so on. Okay. And then what we're going to do is, well, this also plots the contour. We can plot it, I suppose. Contours are just every line is a level set. In other words, this is a set of all points with a particular z value. This is a set of all points with a different particular z value, and so on. So you can plot it as contours or actual surface. Okay, now we get y by applying the activation function on z. Okay. So now we are going to apply the ReLU activation function, which is flat and then takes off for z greater than 0. So what do we expect? So notice that the z is less than 0 at some points and then greater than 0 at some points. So what we expect is that the z will become flat in some regions and then take off in these regions where it's greater than 0. Okay, I'm just going to plot that. Plot y now as a function of x1 and x2. I should say x1, x2. Okay, I'm going to run this. So that's what y looks like. Okay, it's flat and then takes off. And then if you apply a contour, I don't need to rotate this. It's flat here, and then the function increases. Okay. We can, instead of the ReLU activation, we can use the binary activation. Which will look like this, which again kind of looks like the logistic regression case, except with a sharp jump. Again, this y value is equal to 0 when z was less than 0 and equal to 1, when z was greater than 1. And then if you do a contour plot, y is 0 here, y is 1 here, okay? It just plots it. MATLAB just plots it in different colors because they're substantially different. Okay, so that's nice. We are able to get a step, but a step sort of with this. This is what we used to call a separating boundary in logistic regression, I guess. Okay, the classifier. So that's a single layer, like just a single neuron, very similar to logistic regression or the function approximation underlying logistic regression. Let's now do a two-layer network, okay? Two layers, again, not counting the input layer. So let me close all, everything. Now the number of inputs is 2, okay? 2 inputs, x1 and x2. And the second layer, we're going to have 100 neurons. Maybe let's start with 10 neurons, just to keep things simple initially. Maybe 7 neurons, I don't know. So 2 inputs go to 7 neurons, and then 7 neurons go to 1 output, okay? 2 goes to 7, 7 goes to 1, okay? 2 numbers become 7 numbers, and then which becomes 1 number. And then again, just like before, we pick some random weights for layer 1, random weights for layer 2, and the size of the weights matrix needs to be selected in a manner that it's consistent with what the inputs are and what the outputs are, the size of the inputs and the size of the inputs, of course, right? We are sort of doing the linear transformation using matrix multiplication. So if you have a bunch of inputs and a bunch of outputs, the intervening matrix multiplication needs to have the appropriate size, and that's what these things represent. You should slowly go through it to make sure that they are the right size, okay? And then each of the neurons have a bias. So as many neurons as there are as many bias terms, which is the W naught number. And that's just equal to the number of neurons in that layer. Okay, so we've now defined all that we need. Of course, we will have to also define the activation function that we use, whether or not we use an activation function. But other than that, we have everything. We create, again, this mesh grid of meshes. This is now, I'm just going to call this Y grid. We just loop through X and X1 and X2. We should probably call, loop through the rows and columns of X1 grid. The input is X1, X2, I comma J, right? We're just looping through all possible. Maybe I'll show you what this looks like, this mesh grid looks like, actually, just so that if you have never seen it. Let me run this piece. Okay, so if you encounter a program like this and you're not familiar with a particular function, you should dig in and see what that function does by looking at what its inputs are and then what it outputs, okay? So X1 list, of course, is just minus 10 to 10 with 100 points in between. X2 list is exactly the same thing. And then we can apply, let me actually make this thing simpler to understand by making X1 list and X2 list just have 5 points instead of 100 points, okay? X1 list has 5 points and X2 list has 5 points. And then we can go X1 grid, comma X2 grid equals mesh grid. Of X1 list, comma X2 list. And what it does is very simple. All it does is it creates this new matrices now instead of lists, X1 and X2, X1 grid and X2 grids. which have this structure, right? So they are essentially, in this case, they are just transposes of each other, but of course, um, that need not be the case. Let me actually change x2 list slightly so that we can actually see a difference between these things. Okay, x2 list is this, and then let me just do that. Okay, so what did it do? For x1 grid, it just took x1 list and then it made x1 grid have basically x1 list as rows, and then for x2 grid, it took x2 list, which is this thing, and then made it be columns. The useful thing is that if you loop through every I comma j element of x1 and x2, you will have looped through essentially all possible combinations of x1 list and x2 list. So instead of you having to enumerate the combinations, it just allows you to do that sort of in a simple manner. So that's the benefit of this mesh grid. It creates essentially a rectangular mesh. Okay. Okay, so that was just an aside. So that's what mesh grid does, and then we are going to loop through the rows and columns of x1 list, x1 grid, and the input vector to this thing is going to be x1 grid I comma j, x2 grid I comma j, namely the two inputs, and then we are going to say here I've sort of made it a bit more concise. What the first layer does is it takes this input vector, applies the weights, applies the bias, applies the activation function. And then what the next layer does is takes the output of this, which is F1, applies the weights, applies the bias, applies the activation. F2, and that's basically your output, okay? And then let me just run this whole thing. Here we're just plotting, I suppose let me just do this step by step. Okay, so we already get these complicated looking functions, right? That's interesting. Okay, so with just 7 neurons, we got this function which is 0 at some places and then 1 at other places, and where it's 0 and where it's 1 has this much more complex structure, right? So in logistic regression, we could have, of course, planes. We could make the what's called the kernel, like the expression that you put in for z, a polynomial or more nonlinear function to approximate more complex boundaries. In fact, that's sort of what we're doing here. That function comes from a neural network, and you get these much more complex boundary between zeros and ones. Okay. Now that's with just 7 neurons. Let's see 3 neurons. What does that look like? These two are the same functions, so I'm just going to comment this out. Same plot, I guess. Okay, with 3, we just got like this one region. Every time you run it, because our weights and biases are random, every time you run it, it's going to be a different partitioning of the space, I guess. Okay, this is a much more simple thing that arose by random chance. Okay, this was just constant. Okay, so now let's actually make this 15 neurons. Again, we're just making up random neural networks. Nothing interesting there. Okay, so we got a neural network which is 0 at all these places, and then 1 wherever it's yellow. It's an incredibly complex structure here. What this indicates, of course, this is just randomly generated weights and biases, but what this indicates is potentially if you chose the weights and biases in an appropriate manner, you might be able to approximate a much more complicated structure that has pretty fine features, like for instance here, if necessary. Okay, that's sort of the power of neural networks. These relatively simple building blocks can give rise to this complex structure. Okay, so let me stop that there. So next part, what we are going to do is here we just built the neural network by just essentially making stuff up from scratch. On the next step, what we will do is use MATLAB's deep learning toolbox to rather than build these functions like so from scratch and then optimize the weights and biases to approximate a particular relation between input and output. We will just use MATLAB's deep learning toolbox, which automatically has all these pieces built together.